So let's finish up this chapter. All right, remember last class we left off talking about this concept of aromaticity. We had these two rules. In order for a compound to be aromatic, it has to be a fully conjugated ring, and it has to have an odd number of delocalized electron pairs. Right? And aromaticity is like bond conjugation on steroids. It provides this extra bit of stability for these compounds that are aromatic. And the first rule here kind of makes sense, right? We have to have a fully conjugated ring. The electrons have to be able to move around the ring. That makes sense, right? The other rule, though, the odd number of delocalized electron pairs, that seems like it kind of comes out of nowhere. Like, why not an even number of electron pairs? What's the deal, right? Not only that, but we said if a compound violates rule 2, if it has an even number of electron pairs, it is no longer aromatic but anti-aromatic. And in the same way that an aromatic compound is unexpectedly stable, an anti-aromatic compound is unexpectedly unstable, right? So what's going on here with this odd number of electron pairs business? Okay, so in order to explain this, we need to talk about molecular orbital theory. So, what is a molecular orbital? Okay, so when atoms form covalent bonds, their atomic orbitals, right, where their electrons are living, their atomic orbitals will mix together. And this will create new orbitals we call molecular orbitals. Okay, so what is a molecular orbital? Again, if two atoms are forming a bond with one another, they'll take their electron, that shared pair of electrons, right? They're going to take those electrons that are currently living in atomic orbitals, they're going to mix those atomic orbitals together to form new molecular orbitals, and that's where that bonding pair of electrons live. Remember the atomic orbitals, that's that 1s2, 2s2, 2p6, all that business, right? Each atom has electrons living in orbitals. When we take two atoms and we put them together and they form a covalent bond, those atomic orbitals mix together to form these new type of orbitals we call molecular orbitals. Okay, so let's take a very simple example to start out with. We're going to take two hydrogen atoms. Right? And at first we're going to keep them separate. Remember, each hydrogen atom has one electron that lives in a 1s orbital. So I'm going to make this little diagram here of my two separate hydrogen atoms, each containing a 1s orbital. We're going to put a y-axis on this of energy. All right, and we're going to fill in this orbital diagram here. Remember, how do we represent our electrons in these diagrams? Yeah, the arrows, right? So each one has one electron living in its 1s orbital when they're separate. But now we're going to bring these two hydrogen atoms together, and they're going to form that diatomic hydrogen with its single bond. All right, and so what's going to happen is these 1s orbitals are going to mix together, and they're going to form two new orbitals. One of them is low energy, the other one is high energy. Okay, so again, in our diagram here, we have our atomic orbitals. And then in the middle we have our molecular orbital. orbitals. Okay, and importantly, when those two atomic orbitals mix together, they form two new molecular orbitals. All right, this sort of preservation of number of orbitals is really important. The number of atomic orbitals that you mix will always equal the number of molecular orbitals that are formed. And one of these molecular orbitals is lower in energy than those atomic orbitals. We call this the bonding orbital. But the other one is high energy. We call this an anti-bonding orbital. So these two electrons that used to be in this atomic orbital, now I'm going to fill them in my molecular orbital. Okay. Importantly, we have rules for filling our molecular or any orbital diagram. All right, so let's just review that. Filling orbital diagrams. Okay, first of all, you always start with the lowest energy orbital. So which one am I going to start with, my bonding orbital or my anti-bonding orbital? The bonding one, right? The lower energy one. Okay. Rule 2. Equal energy orbitals. Must be half filled first. Then you can go back and double up. And importantly, molecular orbitals, just like atomic orbitals, they have a capacity of 2 electrons. So 2 electrons max per orbital. One is going to be spin up, the other spin down. All right, so these 2 electrons that used to be in these atomic orbitals, now they're going to move into this new orbital that's just formed, this molecular orbital. I'm going to start with the lower energy bonding orbital. I'm going to put 1 electron in. The other electron that I add has to be spin down, so my arrow is going to go in the opposite direction. Okay, cool. So we're going to use these molecular orbital diagrams to help us better understand the difference between aromatic and anti-aromatic. All right? So now we got to draw MO diagrams for aromatic compounds. Okay, so the first one we're going to do is just that go-to example for the chapter, a benzene ring. So, how do we draw these MO diagrams for these aromatic compounds? Here, step 1 is we're going to draw our polygon. In this case, I have a 6-membered ring, so I'm going to draw a hexagon. Okay? And importantly, when we draw that polygon, we need to make sure that one of the corners is pointed down. So draw a polygon with corner pointed down. We're also going to add our y-axis of energy. Okay, so now in my polygon here, at each corner, at each intersection, I'm going to add an energy level at each corner. Okay, so I have this oriented with one of the corners pointed down. So I have one low energy orbital. Let me use a different color actually. Then I have these two orbitals that are of equal energy that are a little bit higher up. Another two up here of equal energy. And then finally one more high energy orbital at the top. Okay, so in my aromatic ring here, those 6p atomic orbitals of my carbon atom form 6 new molecular orbitals in my compound. And the spacing of the energy in those orbitals corresponds to the shape of that polygon. Right? We have one at the bottom, two of equal at one level up, two more even higher, and then one at the tippy top. Okay? How many pairs of electrons, actually how many total electrons are there in this conjugation system in my aromatic compound, if I'm talking about a benzene ring? Right, so I have 3 of those pi bonds. Each one consists of 2 electrons. So we have a total of 6 electrons that we're going to fill in to this diagram. Okay? Where are we going to start? At the top or the bottom? The very bottom, the lowest energy orbital. So I'm going to add one spin up and the other spin down. Okay? Now I'm going to move up to the next level here, but these two are at the same energy. So everybody take a look real quick. Let's make sure that we're filling in these diagrams correctly. I'm going to go through and half fill both of them first. Then I can go back and double up. Whoops, that one disappeared. Half fill first, then I can go back and double up. Okay, so this is the molecular orbital diagram for this conjugated ring system in my benzene ring. And of course, benzene is what? Aromatic or anti-aromatic? Okay, so aromatic. I'm going to be good and label my axis, energy. Okay, so what we did was we drew this polygon. We made sure that it had one of its corners pointing down. We added our y-axis, which is energy. We drew an energy level at each corner of our polygon, and then we filled it in with those delocalized electrons, the correct number of delocalized electrons. All right, cool. So we did one for this aromatic compound benzene. Let's do one for an anti-aromatic compound. This one we established last class was anti-aromatic cyclobutadiene. All right, everybody take a second and see if you can't create the molecular orbital diagram for cyclobutadiene here, given these steps that we just laid out. All right, so I have my polygon. Is it good the way that it is? No, why not? I got to turn it so that one of those corners is facing down. Absolutely. So I'm just going to rotate this. Cool. All right. So now I can put in energy levels for each one of my corners. So I got one down here. I have these two of equal energy here, and then one at the tippy top. And how many electrons am I going to fill into this diagram? 2 pairs, so a total of 4. Okay. So I'm going to start at the very bottom. 1, 2. I'm going to move up to the next energy level, but again, I have to half fill these first, right? So that becomes 3, 4, and now I'm done. I'm all out of electrons. Okay? And so this is the signature of an anti-aromatic compound. These half-filled molecular orbitals. Notice for our aromatic compound, all of those molecular orbitals were fully filled. And for our anti-aromatic compound, our 2 uppermost orbitals were only half filled. Okay? And this will be the case for all aromatic versus anti-aromatic compounds. An aromatic compound will always, any sort of orbital diagram that you draw for an aromatic compound will always have fully filled MOs. And anti-aromatic compounds, you'll always be left with these half-filled molecular orbitals. All right, so this is a direct consequence of our rule that we laid out for aromaticity. This odd number of delocalized electron pairs is what yields those fully filled molecular orbitals. If you have an even number of electron pairs, that's when you get these half-filled orbitals, all right? So that's an direct consequence of the second rule that we laid out for aromaticity. So like, okay, that's all well and good, but what is, like, who cares? What is it about these half-filled molecular orbitals that are so bad? Why does that lead to these higher energy anti-aromatic compounds? All right, so why are anti-aromatic compounds Unstable. All right, well, let's just lay out some of the facts that we have here. This even number of electron pairs results in these half-filled molecular orbitals. Okay? If we have unpaired electrons, they interact with a magnetic field. We call this paramagnetism. All right, this would have been something that you talked a little bit about in Chem 1B. Why are certain metals magnetic and other metals aren't magnetic? It has to do with their electron configuration and whether or not there are any unpaired electrons in that electron configuration. Anything that has any unpaired electrons, those electrons will interact with a magnetic field. Okay. These anti-aromatic compounds, importantly, they did not violate Rule 1, right? So they have a fully conjugated ring. And electrons, any charged particle, when they move in a circle, they generate a magnetic field. Okay? This is something that you may have learned in your physics course. In fact, how does a wind turbine work? How does that generate electricity? It spins this magnet round and round and round, and that's what's moving electrons. Okay? Same thing, the opposite is true as well. If we have electrons that are moving in a circle, they will generate a magnetic field. And we have these unpaired electrons that are then interacting with that magnetic field. Okay? So it turns out that in an anti-aromatic compound, these electrons are moving in such a way that is imparting a force on themselves, raising the energy of that compound. All right? So the punchline here is the magnetic field created by these electrons is imparting a force on them that raises their energy. And this is what leads to our unstable compound. All right, so just to review here, we had those two rules for aromaticity, and the second one was really weird, the fact that you had to have an odd number of electron pairs. And so what we did was we used these molecular orbital diagrams to show that if you had an odd number of electron pairs, you would have a fully filled molecular orbital diagram. But if you had an even number of electron pairs, you would get this half-filled molecular orbital diagram. All right? These molecular orbital diagrams, to be clear, I know it kind of seems like magic. Like, why did you get to just draw a polygon and it worked? It just kind of turns out that that's correct, that we can sort of simplify things using the shape of that structure, all right? And to be quite honest, it's kind of lucky because molecular orbital theory is really a giant quantum mechanical problem. This diagram here is really illustrating some super complicated math involving wave functions and the mixing of wave functions and all that jazz. Something that's pretty cool, but well beyond the scope of our course here. All right, we're just kind of illustrating the punchline here in terms of the energy level of these orbitals that are formed. And because of those half-filled orbitals, the electrons in that ring will interact with a magnetic field. And because they're a ring, the electrons are moving in a circle which is generating a magnetic field, right? So the electrons in those bonds are creating this magnetic field that they are interacting with, and that's raising the energy of those electrons, leading that compound to be less stable than what you would expect. Okay. Cool. So, last thing we're going to do with regard to aromaticity here. Okay, if you remember, we sort of talked at the very end about these carbocation compounds. Let me just grab this and move it over to a new page. Let's do this one. Okay, we talked about these carbocations. All right. But what about if instead of removing that hydrogen and its pair of electrons, we removed the hydrogen, but it left that pair of electrons behind? So we're talking now about a carbanion. All right. We're going to compare these three very similar structures here. So the question is, how do we deal with lone pairs and aromaticity? Okay, so if we were going to determine whether these compounds were aromatic, anti-aromatic, non-aromatic, right? Step one is to go around and make sure that we have a fully conjugated ring. For this first example, we have these 4 sp2 hybridized carbons. But what about this one at the very top? This one's sp3, so it messes up that conjugation of our ring, leading this to be what type of compound? Non-aromatic. Okay. When we got to this carbocation, we said, all right, we're going to go around our ring. These are all sp2 hybridized, but carbocations are also sp2 hybridized. So this doesn't mess up the conjugation of my ring. I indeed have a fully conjugated ring. So now I get to move on to rule 2. Do I have an odd number of electron pairs in this ring? No, because even though that carbocation doesn't mess up my conjugation, it also isn't bringing any electrons to the table. So I just have these 1, 2 pair of electrons. So this compound was anti-aromatic. Okay, so now I'm going to get to this one here, a carbanion. I'm going to go and see if I have a fully conjugated ring. These, all 4, are sp2 hybridized. But what about this one right here? What about this lone pair? All right, so how do we deal with lone pairs when we're talking about aromatic compounds? All right. The lone pairs, they get to choose whether or not to participate in conjugation. So this carbon atom right here, it gets to decide whether or not it's going to put that pair of electrons in a p orbital so that it can talk to its neighbors, or whether it's going to keep it in an sp3 hybridized orbital so that it can't talk to its neighbors. All right, that carbon gets to decide what hybridization to adopt. Okay, so it's going to say, yeah, go ahead and play with your friends. Yes, if that makes the compound aromatic. But if adding that pair of electrons to the ring makes the compound anti-aromatic, the carbon's going to say, no, you can't play with your friends. We're not going to put you in a p orbital. We're just going to keep this carbon sp3 hybridized. So no if anti-aromatic. Okay, so this compound here, we have these four sp2 hybridized carbons. This carbon right here gets to decide whether it's going to allow that lone pair to join the ring. If it does, that will give me a total of 1, 2, 3 pairs of electrons in that ring. So is it going to let it join the ring or no? Yeah, because that will make that compound aromatic. It will give it that odd number of electron pairs. So yes, this carbon here will adopt that sp2 hybridization. This lone pair will be in a p orbital, making this compound aromatic. Okay, so how do we deal with lone pairs in aromaticity? That lone pair gets to choose whether or not it's going to join the ring. All right, it'll do it if that makes the compound aromatic. It's just going to stay out of it if it'll make the compound anti-aromatic. Okay, now obviously these carbons don't have brains. They're not choosing. It's all an energetic sort of thing. All right, but yes, that is the way that I think about it. I think that's helpful. Okay, so let's do another example here. These are really hard to draw, so I'm just going to copy and paste. All right. All right, so now we're going to do the same thing, but with a 7-membered ring. We're going to compare the carbocation to the carbanion. Okay, so step 1, do we have a fully conjugated ring? And then step 2, the odd number of electron pairs. Take a second and see if you can't classify these as being aromatic, anti-aromatic, or non-aromatic. so trying to figure out whether I have a fully conjugated ring. We can see that all of these carbons that are participating in a carbon-carbon double bond are sp2 hybridized, and carbocations are also sp2 hybridized. So this is indeed a fully conjugated ring. I have 1, 2, 3 pairs of electrons, so that makes this compound aromatic. All right. So let's play the same game over here. Again, these these 6 carbons are easy to see that they are indeed sp2 hybridized. But now I got to figure out whether this carbon is. And remember, it gets to decide. And it's going to say yes if that makes the ring aromatic, but no if it makes it anti-aromatic. So I'm going to count my electron pairs. 1, 2, 3. This one would make 4. So is it going to join the ring or not? No. So importantly, that does not make this compound anti-aromatic. It means that this carbon right here will remain sp3 hybridized. So this is non-aromatic. All right, so that lone pair just won't join the ring, breaking the conjugation in the ring, and thus making it a non-aromatic compound. Okay. Now we were talking about carbanions, but there are other elements out there that can have lone pairs as well. So another example of a similar compound, let me just steal this, would be if I have a nitrogen in my ring. So I'm going to replace this carbon with a nitrogen. That nitrogen has a lone pair of electrons, so that lone pair gets to decide whether or not it's going to participate in the conjugation of that ring. Okay, so in addition to deciding whether this compound is aromatic, anti-aromatic, or non-aromatic, I can also ask you about the number of delocalized pi electron pairs, the number of localized lone pair electrons, and the number of delocalized lone pairs. All right, so given this compound here, take a second and first tell me whether it's aromatic, anti-aromatic, or non-aromatic, and then count the number of electron pairs that fall into these 3 categories. right, so again, I'm going to see if I have a fully conjugated ring. These 4 carbons are all talking to one another, but now I get to my nitrogen, and I have to decide whether or not it's going to put that lone pair in the ring. So I'm going to count how many electron pairs I have. 1, 2. That lone pair would make 3, so is it going to join the ring or not? Yeah, so that will go ahead and adopt that sp2 conformation, so that pair of electrons can live in a p orbital, and it can talk to its buddies in the ring. So that makes this compound aromatic. How many pair of delocalized pi electrons do I have? The 2, these 2 right here that were originally my double bonds. What about localized lone pairs? I don't have any in this case because that 1 pair of electrons has joined the ring, and so that pair of electrons is delocalized across that ring. Okay, so we can replace that nitrogen with an oxygen, and now that oxygen has 2 lone pairs. All right, but importantly, we're going to make a note here. Only 1 pair of electrons on an atom can participate in conjugation. Okay, so even though this oxygen has 2 pair of electrons, I'm not even going to look at one of them, right? It can't be that both of them are participating in the ring. Remember, in order to participate in the conjugation of a ring, you have to be in a p orbital. You can't have 2 in the exact same 2 pairs of electrons in the same p orbital. They can't overlap right like that, right? So you can only ever have 1 pair of electrons that is participating in conjugation. So I can say right off the bat, this one is definitely not. But looking at the other one, I'm going to play the same game here. All right, this is these are all sp2 hybridized. That other lone pair gets to choose whether or not it's going to join the ring. If it does, that would make that ring aromatic, so it does. So this is again an aromatic compound with 2 delocalized pi pairs, 1 delocalized lone pair, and then the other lone pair remains localized. Okay. I'm going to pick 2 new compounds, and you're going to fill out this same information for me. All right, so this first one here, aromatic, anti-aromatic, or non-aromatic? Yeah, so this one would be non-aromatic. It's got these sp2 hybridized carbons, but then we got this, at least this lone pair here that we have to decide, so we're going to count 1, 2, 3. If this lone pair joins, it would be 4, so it's just not going to join, right? So this will remain sp3 hybridized, leading this compound to be non-aromatic. Are there any delocalized pi pairs in this compound? Yes, okay. Importantly, this is not a fully conjugated ring, but these bonds are still conjugated with one another, right? The electrons can still travel back and forth and back and forth. They can't make the full way around the ring, so it can't be aromatic, but they still have that perfect spacing, and so indeed, these double bonds are all conjugated, and so those pairs will delocalize. How many localized lone pairs? Both of them, yep. None of them are going to join that ring. Okay, so what about this next one here? This one's a little tricky. Aromatic, non-aromatic, or anti-aromatic? Let's do a show of hands here. Who thinks that this compound's anti-aromatic? What about non-aromatic and aromatic? Okay, cool, everybody's wrong. Let's go through and see why here, okay? So I'm going to go and see if I have a fully conjugated ring, right? This carbon's participating in this double bond, this one is, and because that nitrogen is participating in a double bond, this one is as well, right? Okay, now remember the rule here. Only one pair of electrons on an atom can participate in conjugation. This nitrogen already has a pair of electrons participating in conjugation. It cannot possibly lend that lone pair to the ring as well, right? It's already got a pair of electrons in a p orbital, so it doesn't even have the option of putting that lone pair in the ring. So we can just note here for this one, this lone pair must be localized. All right, doesn't even have the option. So then we're just going to say we have a fully conjugated ring. There are 1, 2 pairs of electrons in that fully conjugated ring, making this compound anti-aromatic. It's got 2 delocalized pi pairs and 1 localized lone pair. No delocalized lone pairs. All right, so again, this compound here, we got to go back to that rule that only 1 pair of electrons on an atom can participate in conjugation. Okay, cool. All right, so now we're going to finish up by just talking about a few reactions of benzene. All right, so importantly for alkenes, so if we take, for example, cyclohexene, we learn that alkenes undergo a particular class of reactions. So for example, here if we react it with HBr, we would get the following product, where a hydrogen is added to one carbon and a bromine is added to the other. All right, we had a lot of reactions of alkenes that followed this same sort of pattern here. What class of reactions do we call this? Not substitution or elimination, but addition, right? So alkenes, they undergo addition reactions. Looking at benzene, so now I'm going to do the exact same thing, but I'm going to add 2 more double bonds to that ring. So I'm no longer talking about a cyclohexene, but now we're that special benzene compound. So if this underwent an addition reaction, this would be my product here. All right, but importantly, what we're going to see is that benzene does not undergo addition reactions. This is not the type of reaction that we see for benzene rings, because in order to undergo an addition reaction, it would have to lose its aromaticity. It goes from being a nice, stable aromatic compound, but when it gives up that double bond, now it's non-aromatic. Okay, so benzene does not undergo addition reactions. Because it doesn't want to give up that aromaticity, that super special aromaticity. So indeed, we're going to see that all of our reactions of benzene preserve that aromatic ring. Okay? We're going to spend all of next week on a particular class of reactions. All right? For the end of this chapter, we're going to kind of throw in a few random ones here. So the first set is going to be reactions that occur at what's called the benzylic position. So remember, for alkenes, let's just take our examples here. We had a special name for this position right here. 1 carbon removed from the double bond. What was that called? The allylic position. All right, for benzene, similarly, if you're 1 carbon removed from that benzene ring, this is what we would call the benzylic position. Our first reaction is going to use a reagent we've seen before. Okay, so if we had an alkene and we treated it with NBS, does anybody remember what NBS is doing for us? Say it again. It's not a reduction, no. This is what we call an allylic bromination reaction. where this NBS reagent here, it sticks a bromine on the allylic position of your alkene. And we're going to see it does the analogous thing to a benzene derivative, what we would call benzylic bromination. Where it sticks a benzene on that benzylic carbon. Okay, so we're talking about reactions that occur at the benzylic position. What is the benzylic position? Well, it's analogous to the allylic position in an alkene. A benzylic carbon is one that's one removed from that benzene ring. And our first reaction uses this reagent NBS, which we saw before in allylic bromination reactions. And for our benzene derivatives, it's doing the analogous, it's brominating that benzylic position. Okay, our next reaction utilizes sodium dichromate followed by a strong acid and water. Okay, and when we see chromium in our reagent, what do we automatically think? Does anybody remember from last semester? We sort of threw it in at the very end, all right? If you see chromium, you think oxidation. And in Chem 1B, you sort of learned how you calculate oxidation numbers and all that jazz, all right? But in organic chemistry, we said that we can simplify it a little bit. Because when we're talking about oxidating a compound, we're talking about adding more carbon-oxygen bonds. And so this will oxidize this benzylic position, maximally adding as many oxygens as it can. So this fully oxidized benzylic carbon is now a carboxylic acid. Okay, so again, focusing on that benzylic position, if we treat it with this oxidizing agent here, we will get a fully oxidized benzylic carbon. So it's got as many oxygens as you can put on there, right, making it a carboxylic acid group. One of the quirky features of this reaction here, let's say instead of taking this methylbenzene, this toluene, we took butylbenzene. Now it's got a big chain on there, and we treated it with this same reagent. Well, it is going to chop off all of those other carbons and give you that exact same carboxylic acid product. All right, so even if you got a bunch of other stuff going on, you will still fully oxidize that benzylic carbon. All right, the one exception is if your benzylic carbon is a quaternary carbon. Then you will have no reaction. right, we're not going to learn the mechanism of this reaction here, but it just turns out that you need at least one benzylic hydrogen. What's up?
I think I'm in around class 3.
Cool. All right, so we learned about these two reactions of our benzylic position, right? First of all, this benzylic bromination with NBS, where we stick a bromine on there. The other one is an oxidation of that benzylic position, creating this benzoic acid, right? Fully oxidizing that benzylic carbon. All right, so then the last reaction that we're going to do here is the reduction of a benzene ring. All the way to cyclohexane. All right, how do we reduce our alkenes? What do we add? Yeah, platinum, palladium, some metal catalyst, right? So same thing here. We're going to have hydrogen gas. The go-to metal catalyst is nickel for this one. But our benzene is far more stable than our other alkene compounds. So it turns out that in order to efficiently reduce this benzene ring, you got to use some pretty extreme conditions. A pressure of 100 atm, so 100 times the pressure of the current atmosphere, the room that we're in, right? You got to really crank up the pressure, and the temperature gets cranked up to 150 degrees Celsius. So very similar to what we saw before, but just more extreme conditions to get that benzene ring to actually reduce. And this kind of checks out within the context of everything that we learned, right? Benzene requires these harsh conditions to reduce because it's so much more stable than a normal alkene. Okay, and so we're going to keep it at those three reactions for this particular chapter. Again, next chapter we'll talk about a new class of reactions that occur for benzene. Just to kind of give you a preview here, like we said, the benzene does not undergo addition reactions. So for bromine, if we take bromine, we'll talk about we have to actually use a catalyst as well. You don't see an addition reaction. What you see is instead a substitution reaction, where you're going to swap out one of those hydrogens on your benzene ring for one of these new compounds here, for one of these new groups. All right, so as we said, benzene doesn't undergo addition reactions. Instead, we'll talk about these substitution reactions for our benzene ring. That's what next chapter is going to focus on. Okay? So again, for this one, we wanted to throw in these kind of random sidebar reactions for benzene, specifically the reduction of benzene all the way to cyclohexane. We need some pretty harsh conditions to do it. And then we have these two benzylic reactions here, the benzylic bromination and the benzylic oxidation reactions. Those are the three that we're going to cover in this chapter. Cool? Break.